Today we're going to be learning about 2's complement binary. Now let's have a think about the numbers that we've looked at so far. Everything that we've seen has been dealing with positive numbers. We haven't looked at how negative numbers might get represented. And it should be obvious that computer languages and systems will be quite useless if they can't store negative numbers. So computers need a method to represent whether a number is positive or negative, and ideally store that in the same memory allocation as the number itself. To be able to represent negative or positive numbers, the most significant bit is reserved for the sign bit, with 0 representing positive and 1 representing negative. So the most significant bit is the first bit. If I think about the number 101001111, we could think of this as that number there, with our first bit stating whether it's negative. So we could call this, one system would be to call this negative 39, knowing that this is a 1 plus a 2 plus a 4, no 8s, no 16s are 32. So 32 plus 4 plus 2 plus 1 is 39. And we ignore this. We don't give it the 128 value. Instead, we call it the positive or negative value. And so we give this value negative 39. That's one way of storing negative numbers. It has a few problems. And so this is what we just call signed magnitude, and we don't actually use it very often. What numbers could we store with this? Well, it's clear that a normal 8-bit number of unsigned gives us numbers in the range of 0 up to 255. Using this that we'll call signed magnitude, we can't go up to 255 anymore because our top bit is reserved for the sign. So we can only go to 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which tells us our maximum is 127. And our minimum is going to be the same value, but negative, since we can imagine that we've got a 1 out the front here, giving us a negative. So this gives us a range of negative 127 up to 127. So if we think how many numbers we can represent, 8-bit gives us all the way up to 255, including 0. So that's going to give us 256 numbers. And how many? What about this signed? Well, we've got 127 on one side of a 0, 127 on the other side of 0, and then plus 1 for 0 itself. That gives us 255 numbers. Why have we lost a number? Now, if you think about it, it should be obvious that what's actually happened is that we've got two different ways of representing 0. We've got 1, 2, 3, 4, 5, 6, 7, 8 zeros is one way of representing 0. And we've also got 1, 0, 0, 0, 0, 0, 0, which is negative 0. But we all know that negative 0 and 0 are exactly the same number. So these two numbers both represent the same value. So we've lost one. That's one reason why signed magnitude isn't a perfect system, and there's a few other reasons as well. So we've actually got a new system that we're going to use. And the new system that we use is something called 2's complement. It's a really important system, and we're going to be studying it quite a lot now. We usually write it like this, 2's complement. One way to think of 2's complement is if we imagine our number line and we've got sort of 0 up to 127 there. Since we've got an extra digit, we want to represent all 256 digits and we don't want to have a double representation of 0. Let's make this number here 1000000. Let's make that refer to negative 128, and then we'll count upwards from there. Instead of being our standard negative number representation where we've got 1, 2, 3 going up there and negative 1, negative 2, negative 3, this has some problems in that bigger numbers, our definition of x is greater than y, bigger numbers usually mean that they are to the right of each other on the number line. But this is very difficult, certainly for primary school kids, if you ask the question of negative 3 and negative 1, which one's bigger? Now, we all know that negative 1 is bigger than negative 3 because it's to the right on the number line, but that's a fairly difficult concept to understand. And 2's complement actually changes the way that we think about those numbers. And so our smallest negative number that we can represent, meaning the most left number, is given a 1 with a bunch of zeros afterwards. And we count upwards from there. So increasing this number, so for example, 100000001 is actually negative 127. We've increased this number, the bit after there, and so we're moving to the right on the number line. It sounds really complex, and you really don't need to know all those technical details about it. There is one massive advantage to 2's complement, which we're actually going to talk about later, and I'm not going to worry about explaining one of the major benefits of it just yet. We'll save that as a surprise for later. Right now, the skill that we're going to look at is how do you write a number in 2's complement. For example, if I have the number negative, if I want negative 24, what's that going to look like in 2's complement? We know that we're going to, in an 8-bit 2's complement, we're sort of going to start at negative 100000000. That's this number up here, and count forwards. But how far do we have to count? It sounds like there's going to be a lot of complex maths, but it's really quite simple. And there's a step-by-step guide, which is given to you in your textbook, but we're going to start, I'm going to give an example of that. To make a 2's complement, there's a fairly simple process that you have to go to, and it starts with what's the positive equivalent. So if we're trying to find the number for 24, I'm just going to think about what the normal 24 looks like, which is going to be 0, 0, 0, 1, 1, 0, 0, 0. That's a 16 and an 8. 16 plus 8 is 24. All right. Now, to take the negative, to find negative 24, I take that positive and I go through 3 steps. The first step is that I start at the right and work to the left. The second step is that any 0 bits stay as 0 bits until I get to the first 1 bit. So these 3 here are going to stay as 0 bits. And then the first 1 bit also remains the same. From there, still working to the left, everything gets flipped. So I'm going to turn this into 0, 1, 1, 1. That gives me an output of 11101000, which is negative 24 in 2's complement. One of the beauties about this system is that it works both directions. So if I've got something like 11111010 and I want to work out what that is, I'm going to do exactly that same process that we did to get the positive number. So I'm going to start at the right. Any zeros stay as zeros until I get to the first one, and the first one also stays the same, and then I flip every bit afterwards. This turns it into a number that I can easily read. In this case, the units column, the 2's column, the 4's column. 4 plus 2 gives me 6. And so this number that I started with must be negative 6. That's how you do a 2's complement conversion. This is a pretty complex topic. It's okay to rewind the video, watch it again, see what I do a few other times. And there's plenty of notes given to you in page 16 of the textbook. So do have a read of that and have a go at doing some 2's complement conversions. Thank you.